Come on in, everyone. Hope everybody had a wonderful July 4th weekend. We're about 2 minutes early, so feel free to ask me any questions if you want. Of course, when class starts, I'm going to you'll still be open for questioning, but start early. No questions? That's cool. Got about 1 more minute. We only have 4 of you in here so far, so hopefully more will come up. Here's the 5th. Ooh, and we got 6 on a roll down. All right, well, time's about up, so I guess we'll go ahead and start. Again, does anyone have any questions about past homeworks or past material, tests, anything like that? I have some announcements regarding tests as well to make, but to make sure no one has any problems they need help with, topics they need help with, or just general class information. Okay. Oh, another person came in. Woohoo! Another one down, and another one down. Another one comes to class. I sound just like him, don't I? Thank you, Mars. Name down. Lead singer for Queen. Dead now. Dang, picture his face, can't think it. Oh well.
Freddie Mercury.
That's it. Thank you, Freddie Mercury. God, that was going to bother me the whole class. I just sit here making mistakes and writing Mercury in for various answers or something crazy. So thank you. You saved the class. All right, a couple of you just came in. The class has already started. I did ask if anyone has any questions on any past material, tests. I have some announcements regarding tests, but do you have any questions about topics that we've covered, about how the class has been running or anything like that? Okay, looks like we're good on that. So what I wanted to let you know is that I've decided to make Wednesday. Of course, we were supposed to have today was supposed to be a test day, if I remember correctly, in lab, but I pushed it back. I got Mr. Mitchell to push it back as well. I think he was going to do something kind of different with you. So hopefully I had a good day at lab. Mr. Mitchell's fun that way. But anyways, we're going to have a test on Wednesday, not Tuesday, not Monday, but Wednesday in lab. But we're also going to have another test. So today, or first thing tomorrow, you should see 2 practice tests come up. I hadn't at this point decided whether I'm going to do the next 2 chapters on the online test or the next 2 chapters on the face-to-face test, and then the online test will be the chapters after that. Haven't decided yet. Might even do 3 chapters in each test or something like that. So anyways, all that stuff's not decided. That's why I haven't posted it yet, but I will post it. And what's going to happen is Wednesday, we will have a test. And by this afternoon, I'll let you know specifically what that's going to be on. And then you'll have a test that's online that's probably going to be due probably by Friday of next week, something like that, but maybe I'll make it Monday. Okay. So I want you to have plenty of time with the practice test, that sort of thing. And like I said, it might span 3 chapters instead of just 2 like normal. I'm not sure, but we'll figure something out. And I'll post the test. When you see the test posted, I'll actually email everybody, or at least make an announcement and send that announcement to everyone. But by clicking on the test, you'll see how many chapters are covered and that sort of thing. So I might not take the time to write out all the sentences and all that good stuff, because sometimes I'm just tired. So any questions on that before we get started? Okay, well, we more or less finished chapter 9, which was on momentum. I wanted to do a couple center of mass problems for you. And then I'm going to jump into the chapter on rotational motion. And we're actually in a pretty good space time-wise, so I've got sort of plenty of time. I might not finish all of the chapter on rotation tonight, but the main thing is we'll have a good introduction to it, and I'll actually work one really robust Atwood machine problem. I'll call it the daughter of all Atwood machines, because I did one in class today that was horrible, and I named it the mother of all Atwood machines. And that was in my lecture class. It was really it made for some ugly parts because it had 2 different radii, 2 different frictions, all sorts of crazy stuff. So I'm gonna make a little simpler one, and you guys can benefit from that, but so will the other classes. And you probably don't want to see the other one. It was not a lot of fun, but I mean, it was fun for me because I like doing a lot of algebra, but that's just not normal. Most people aren't like that. So what I'm going to do is open up a new quote unquote notebook in my good notes. I really am. A new one. Okay, and I created it. I'm going to title it later because I ain't worried about that. And I'm going to share it. So let's share screen. My little tips screwed in properly. I'm so smart. I'm no longer a senior citizen. And I mean that jokingly. A lot of senior citizens are way better off than me. Mr. Rogers window. And now all of a sudden my iPad's deciding to send me all the text messages I've received since the last time I was on here. All right, so first off, I'm going to imagine a plate. Okay, evidently I'm writing with the eraser, so that's not a good thing. First thing I'm going to do is draw a coordinate system. And then I'm going to imagine a plate. And this plate is 3.00 meters by 3.00 meters and has a mass equal to 10.0 kilograms. Now, right here at 0.500, and this, by the way, all these units are going to be in meters, and 0.500 meters. Everything's going to have 3 sig figs, and everything's going to have units of meters and kilograms. I'm going to have mass 2. Okay, and I'll say mass 2 is equal to 50.0 kilograms. I'm going to say right about here at, let's say this is 2.00 meters and 1.00 meters. I'm going to have a mass 3, and mass 3 is going to equal 70.0 kilograms. And let's say right over here at 2.50 meters and 2.75 meters, I'm going to have mass 4. And M4 is going to be 80.0 kilograms. The plate is uniformly distributed. So it's a uniformly distributed mass. So there's a lot of different ways about thinking about that. One way you could think of it is the dead center, the geometrical center is the center of mass. And that's really what we're trying to get at here, is that we know where the mass is acting. The mass of the plate is acting right at 1.50 meters by 1.50 meters. But if you cut that in half, then the right half would have its center of mass at the geometrical center. And if you cut that in half, the top half would have its center of mass at the geometrical center. And you keep on doing that, no matter how many times you split it up, it's always going to be the geometric center is the center. So that's one way of looking at it. Another way of looking at it is just the density, whether you're talking about a 1 centimeter piece by 1 centimeter piece, or whether you're talking a 3 meter piece by 3 meter piece, the density is always going to be a constant. Okay, so when we say uniformly distributed, that's what we mean, is the density is always a constant. So we could say, for instance, the density in this case, since it's just an area, I would say the density is sigma, and it would be 10.0 kilograms over, obviously this is 3 times 3 would be 9.00 square meters. Okay, and any part you cut off would have that. Now, if I was doing a volume where it was 3 dimensions instead of 2, I'd say rho, and that's mass over volume. Or if I was doing just a rod, I would say lambda, where that's mass over length. So just keep that in mind, because that's some of the stuff we're going to have to do. Now, the formula for the center of mass, x center of mass, is equal to m1 x1 plus m2 x2 plus mn xn, all that divided by m1 plus m2 plus mn. Okay, and y is done the same way, except you put in y's there. Okay, so let's calculate the x center of mass. So the x center of mass, since this is uniform, we know the plate is going to act as if it's at 1.50 meters in the x direction and 1.50 meters in the y direction. And that's the direction that we actually made in this coordinate system. Okay, so I'm going to say 10.0. I'm going to leave off the units just for space. I don't know why I'm writing in red. All of a sudden, I know I did it to make arrows on the axes. But anyways, 10.0 kilograms, 1.50 meters in this case. I said I'm going to leave off the units, but I wanted to show you at least one of them so you know what I was doing. Plus, now mass 2 is 50 kilograms. So I'll put the unit on that one too, so you understand. At least when you look back, you'll have one set with units on it. Now the 50 kilograms, this could have been another rectangle or square, and you would then have to be required to figure out the center of mass of it and say that's where it's acting. So this problem could have been a lot bigger. Instead of me putting a dot there, I could have put a square, and I might have pointed to one corner, and then you'd have to figure out where the center of mass is and figure out the x center mass for that one and the y center mass for that one. If it's uniformly distributed, again, that just means it's the geometric center. So if you have a rectangle, it would be on the crosshairs of the two, or where the two diagonals cross. But in this case, I actually gave it to you as if they're point particles. This one's at 0.5 and 0.5, so 0.500. As I told you, I'm going as if everything has 3 sig figs. Plus the next one is 70. I'm leaving off the sig figs now just to fit in the space. The 71, which is number 3, has an x coordinate of 1. And then the 81 has an x coordinate of 2.5. I know that's really bad because I fit it all in there. So 10 plus 50 would be 60. Plus 70 would be 130, plus 80 plus 130 would be 210. So that's 210 kilograms. Now I do all that math, which is 10 times 1.5 plus 50 times 0.5 plus 70 times 1 plus 80 times 2.5. So hopefully everybody can read that. I can hear that if they at least couldn't read it. I will put here just to make this a little more clear that this is 80.0 kilograms times 2.50 meters. Okay. So when I do all that, I get 310 over 210. This is 310 kilograms times meters over 210 kilograms. And that gives me 1.476 meters. And I'm going to underline that 6 because according to sig fig rules, I shouldn't have it. So does that make sense to everyone? So that means it's a little bit less than the center because the center of the uniform disk was actually right at exactly 1.5. So it's a little bit left of 1.5. So we could say the x center of mass is somewhere. This is like 1, 2, 3, 4, 5, 6.5. So 3.25 would be the center. That's 1, 2, 3. So it's a little bit less than 3.25. That means the x center of mass would be somewhere along that line. Roughly. Okay. That just gives you a ballpark figure. Now let's do the y center of mass. So again, we'll start with 10.0 times 1.5 because that was a uniform mass plus 50. And the 50 was located at 0.5 as well. Plus 70. 0.0, and the 70 was mass 3, and in the y coordinate that was at 2.00 plus 80, and that 80 was at 2.75 meters, and all of this will be over 210 again. So I get 10 times 1.5 plus 50 times 0.5 plus 70 times 2 plus 80 times 2.75. That gives me 400 kilogram meters over 210 kilograms. So that gives me 1.905. Actually, when I want to carry one extra digit, if that digit rounds to 5, I carry 2 just to be safe. So that's 1.9047 meters. So that would be somewhere along, let's say right along here, maybe. That would be YCM. So the center of mass should be roughly at that spot right there. In other words, if we wanted to balance that plate, that's where I'd stick my finger and it would balance. So that's what the center of mass means. Not only that, if I were to take that plate with those masses secured to it, say they're actually glued to it or made into it or whatever, and I grabbed it by one corner and I just underhand, slow pitch softball pitched it, the part that would actually follow a parabola would be that little dot that's the center of mass. And in principle, I could say, I could predict where that bottom right corner would be at any point in time just by knowing what the orientation of the plate was when it left my hand and what the rotation rate I gave it was. So I could predict exactly where that corner is, or any other corner for that matter, at any point in time. And I could even predict, you know, whether it's going to land flat side down or a particular corner down, or whatever. So that's really what we're lacking right now, is that ability to do the mathematics associated with rotation. But in principle, what we now have is the ability, once we cover that other material, to actually, you know, work out what rigid bodies do. In this case, we're pretending that body's rigid by assuming that the masses aren't moving with respect to the other masses. The distance between 3 and 4 is always going to be the same, and it's always going to have the same angle. The line from 3 to 4 is always going to have the same angle with respect to the vertical as it does now. So that's sort of what we mean by rigid body. So any questions on that? So I just wanted to show you one of the typical center of mass problems you could solve, but I also wanted to show you one that was really discrete. Now I'm going to show you another one that's not discrete. So if we wanted to find, for instance, the center of mass of a more complex shape, I'm going to say, let's imagine first I have a coordinate system. Like that. And now let's imagine that I have a circle. I was supposed to be a circle jerk. My circle was so bad it made it into a parabola. That stinks. Okay, let's see if I can do a little bit better circle. No, I cannot. No. Okay. What I'm going to do is this. Whoa, evidently I'm going to move this axis just because I can, which I was unaware of. Oh, I hate it when this happens. Okay. So now I'm going to try to draw a circle. Okay. Now I have a circle. Whoa. Why can't I just move that? Ugh. Okay. I'm going to say that circle has a radius r and it's centered on that origin. It clearly is not, and it's a half circle. Okay. I hate my life. This is not, no, stop it. It's doing everything wrong. I'm not stupid. Let's see. If I do it again, it's going to be a good one. This time I feel it. What? You didn't correct that? There we go. That looks good. Okay, now what I'm going to do to make this realistic is cut the bottom off. Okay, so now I've really got the system said, you darn it. Why doesn't it know what I want to do every time I want to do it? Okay, stop laughing at me. So this is going to be our x-axis, and this is going to be our y-axis. All right. So what I'm saying is this is a circle of radius r, and the mass is m, is uniformly distributed. Now, again, this is just an area. It's not a full volume. So I'm going to use that sigma to represent the density. So in this case, the density would equal m over, or 2m over pi r squared. Notice it's 1/2 pi r squared because it's a half circle. That's all. Okay. Now, I want to calculate the x center of mass. And the x center of mass is equal to the integral of x dm over the integral of dm. Similarly, the y center of mass is defined. Okay, so I've always taught my students that when you go to do an integral like this, you want to make sure the integrand, which in this case includes the x and the dm, you want to make sure that does not vary by more than an infinitesimal amount in the variable x. So I need to choose an infinitesimal differential mass element. Well, what we know is we can use dm is equal to rho dv. I've mentioned this before, r sigma dA r lambda dl. Those are the three scenarios. I'm doing the sigma dA, and that means I need, since I have a sigma here, that's a constant. That's what uniformly distributed means, is the density is a constant. So I'm going to use sigma dA, but that tells me I need an area. So what I'm going to do is I'm going to come over here to X and draw a little rectangle whose thickness is dx and whose height y is equal to square root of r squared minus x squared. Okay, does that make sense to everyone? So now I'm going to go ahead and do the top integral. That's going to be the integral of x times sigma dA, which equals the integral of x times sigma times, now we have square root r squared minus x squared. Okay, that's the height y times the width dx, and I'm going to integrate this from x equals 0 to r. Okay, now to do this, I'm going to say let u equal r squared minus x squared, then du is equal to negative 2x dx. Okay, I've got an x there already, but I don't have a negative 2. So what I'm going to do is I'm going to say this will be negative sigma over 2. That way I can multiply by negative 2 inside and change that x times dx into a du. So now I have the integral of u to the 1/2 du. That integral, of course, is 2/3 of u to the 3/2. So I'm going to get negative sigma over 2 times 2/3. And the way I can do this is actually I'll do another bracket. I'll say this is r squared minus, now in this case, the top range of integration was r, but that's to the 3/2 power, minus r squared minus, in this case, it'd be 0 squared. And again, that's to the 3/2. So what I just did was I carried out the integral at the ranges of integration. In other words, I substituted the fact that u was equal to r squared minus x squared, so that the integral was 2/3 u to the 3/2 power. So I just plugged in x equal r and then subtracted from that the case for x equal 0. So you can see that this first term is completely 0, which is nice because that fixes that negative, because we didn't really want a negative in there necessarily. And of course, the next one turns out to just be r squared to the 3/2, a negative of r squared to the 3/2. So I get positive sigma over 3, and then times r cubed. So that's the top integral. Now the bottom integral integral of dm is exactly the same, except I don't have that pesky x, okay, which actually was a lifesaver because it kept us from doing a trig substitution. So I can say the integral of sigma, oh, so it's sigma dA, and now we have the square root r squared minus x squared dx. Now you can look that up in a table of integrals if you want, or you can work out basically the you can work out a trig substitution. Let me try that real quick. If it goes south, it's no big deal. You probably learn a little bit from it anyways. So we're going to say let x equal r sine theta, then dx would equal r cosine theta d theta. Okay, so when I do that, I'm going to get integral, sigma is going to be out in front. Now I'm writing in green. I want to go back to blue. So I'm going to say sigma's out in front, integral of, now I've got the square root of r squared times 1 minus sine squared theta. And the reason why I substituted sine was because you can see it's a 1 minus. If it had been a 1 plus, I would have used tangent. And then, of course, dx is equal to r cosine theta d theta. And when x is equal to 0, that would mean theta is equal to 0. And when x is equal to r, that would mean theta is equal to pi over 2. Actually, okay, so that should work. Now my integral becomes sigma, the square root of r squared just is r, so I'll put an r out front. And then I've got an r there already, so I'll put another r out in front. So now I have the integral of 1 minus sine squared is cosine squared. Cosine squared square root is just cosine. So I got cosine times cosine, that's cosine squared theta d theta. Now, this is a valuable, or this is an easy integral because we can use a half angle formula. And I'm just going to double check. I think it's 1 plus sine of 2 theta. So I'm going to double check that. Let's see, integral, no, trig identity, cosine squared identity. Yeah, cosine squared is 1 plus cosine 2x over 2. So I'm going to say now this is equal to sigma r squared times the integral of 1 plus cosine 2 theta over 2 d theta. So my memory was wrong in that I thought it was sine, not cosine. But yeah, that's pretty good. All right, so that's not too bad of an integral. We can go ahead and say that's equal to sigma over 2 r squared, integral of d theta from theta equals 0 to pi over 2 is going to be pi over 2 minus 0 plus the integral of cosine 2 theta. We can treat that like it's w. So I can say that's the cosine of w, and then dw would be 2 d theta. So I need another 1/2 there because I got to multiply it by 2, and to multiply it by 2, I got to multiply it by 1/2. So I'll put a 1/2 here. And now I'm just doing the integral of cosine theta d theta. We know that the derivative of sine is cosine, so the answer should be just sine. So now I'm going to say the sine of 2 pi over 2 minus the sine of 2 times 0. Okay. So in this result, I get sigma over 2 r squared times pi over 2 plus, now over here, what do I get? I get the sine of pi, which is 0, and the sine of 0, which is 0. So that's plus 0. So XCM is clearly sigma over 3 r cubed divided by sigma pi r squared over 4. Does that look right to everybody? I didn't make any boo-boos. So that gives me 4 over 3 pi r. Okay, now I'm bothered. Oh, no wonder. Boop-a-doo. Hey, am I supposed to integrate from x equals 0 to x equal pi r? Asking for a friend here. What am I supposed to integrate from? This is actually exactly the right answer for when I do the y. I knew by symmetry this was supposed to come out to 0, but I did the wrong range of integration. The range of integration should not have been 0 to r. It should have been negative r to r. Y'all see that? So everything is right mathematically, but when I said theta x equals 0, that should have been x equal negative r. And that would have given me, let's say, sine of theta has got to equal negative 1. So that could be 3 pi over 2. So x equals negative r implies theta is equal to 3 pi over 2, because remember, sine looks like that, right? The negative 1 is right here, which is 3/2 pi. But x equal r, that does give me theta equals pi over 2, so that one's fine. So let's see what happens when I do this. So all that really should happen, I'm going to write this in red over it so we can track what it's supposed to be. I said theta was 0 when x was 0. Now I have to say theta is negative r. So this should be negative r here. And then this part is pi over 2 minus r. That's acceptable. And then theta equals r still gives pi over 2. So this is okay. But sine being equal to 2 times the sine of 2, 0 is not right. This is actually supposed to be 2 times 3 pi over 2. So that's the sine of 3 pi, which still gives me 0. 1 pi, 2 pi, 3, yeah, it's still 0. So this part is still 0. But this part becomes sigma over 2 r squared becomes pi over 2 minus r that part's okay. And then when I do that over here, this part becomes r squared minus r squared. This is okay. But this part becomes negative r squared. So in fact, in this case, I just get 0. The good news is I can change it with those little things there just because I did this part wrong. So the corrections are all down there shown. The good news is we've worked out all the details for the y part, which is what I'm going to do next. So I guess me doing the y part was seeming fairly rational when I was actually doing the x part, because it looked just like what I did when I did the y part. So maybe that's what happened. But you see now, because of that r being negative r in the bottom, you actually get 0 for the numerator part of the x center of mass. And the other thing becomes something that's not necessarily that helpful. I think that's right. We might have to do it again. I mean, we're supposed to use it again when we do the y center of mass, but in this case, it's I'm hoping that's right. So now I'm going to do the y center of mass, and that should make some sense. Does everybody follow what part I did wrong and how the corrections I made, or would you like me to do it again from scratch? I don't mind doing it again from scratch, but the more important thing is that you understand how we did it. So me screwing up with that range of integration was bad, but I will gladly completely do it again. But I think you might be able to follow it by me showing you what parts are correct and what parts are wrong by showing them in red. And I'm going to write over here, corrections in red below. Okay. So does anybody want to go ahead?
Sorry, somebody had asked why you switched the bounds to negative r to r.
Okay, so I have to go all the way over to here and then all the way to here. I was just going from here, which if I'd done a quarter circle, I'd now know the right answer for a quarter circle. The center of mass of that would be 4/3 pi. So we got an extra problem in there. I'll pretend like that's the positive takeaway of this. But if I had that thing and this is r and this is r, then I know the center of mass would be along 4/3 pi times r. And from symmetry, I suspect it'd be the same thing here as well. 4/3 pi times r. So that's what I actually did by going from 0 to r instead of negative r to positive r. And thank you for letting me know that, because when I'm on the screen, I do not see my chats. And in fact, I don't see them. Let's see if I can.
I have another question.
Go for it, Nora.
So we just solved for the center of mass in the x direction, but for y, wouldn't it just be r? Because r is the center, like, or it would be like r/2 because you're
seeing symmetry, but you're getting the two symmetries mixed up. If you see the y-axis, if I replace, say, the right-hand side with a mirror, say at 45-degree angle, then the mirror image of the left-hand side would look exactly like the left-hand side. So you can tell that that y-axis is a symmetry axis. So you know the center of mass has to be along x = 0.
Yeah.
That's why when I got something other than 0, I realized I'd done something wrong and saw that it was the center of or the range of integration that screwed up. Now this other one, you can see most of the weight is down near y = 0. So I'd expect it to be closer to the bottom, but definitely not r.
Okay, got you. So we were.
Yeah, go ahead.
Oh, we were just assuming that since it's symmetric, we don't need to solve for the y coordinate. We're just solving for the x coordinate. Because I'm not entirely sure what the purpose of that would be.
Okay, so I'm trying to find where on this half of the pizza would I try to carry that out as a waiter. Okay. If I could only carry it with one finger, then my guess instinctively, assuming we have a plate that has the same shape, okay, my guess would be instinctively it would be somewhere along that y-axis is where the center of mass is, and then I'd guess that somewhere closer to the origin but still above the x-axis is where I'd have to put my finger vertically, and then I could balance it there. That's what we're looking for, is the balancing point. What I just did, and I think I really need to go over it again just because of the mistake I made. What I just did was showed that the center of mass was exactly what we expected at x equals 0.
Oh, okay. Gotcha. I didn't see where you put x equals 0. That's why I was confused. I thought
Yeah.
it was the sigma over 2 r squared.
Yeah, let me
Sure.
sort of redo that. We're going to say integral x dm over integral dm. I'm in green now for some reason. So the integral x dm is going to be sigma square root r squared minus x squared, like that, times dx. So this one, we were lucky, we could say let u equal r squared minus x squared, then du would equal 2x, negative 2x dx. And then I integrate from x equal negative r to positive r. And from the symmetry of that half of a pizza, we'd expect it to be at x equals 0 because obviously the right half and the left half are identical. And the mass is uniformly distributed, so you expect it to be there. So we're hoping this comes out to be 0, not the denominator, but we hope the top does, or somehow the two mix together and make 0, but clearly it should be the top comes out to be 0. So that's going to be equal to sigma times the negative, actually, let me do this. That's going to be negative sigma over 2, because I need a negative 2 in front of the x in order for the substitution to work. So I'm multiplying by negative 1/2 and multiplying by negative 2. And then I have the integral of u to the 1/2 du. And when x is equal to, actually, I'll just keep this one and we'll plug back in x squared and r squared and all that good stuff instead of changing the ranges of integration. I'm going to say now that's equal to negative sigma over 2. The integral of u to the 1/2 is u to the 3/2 divided by 3/2. So that's going to become 2/3 square root r squared minus x squared. And that's evaluated from x equal negative r to positive r. And in this case, the 2's cancel out. I'm going to get negative sigma over 3 times the square root r squared minus r squared minus the square root of r squared minus r squared, which is clearly 0. So that's really what happened. But because I didn't do my range of integration right the first time, that made it really confusing. This isn't written that clearly. I'm going to go ahead and write it again. Negative sigma over 3 square root r squared minus r squared minus the square root r squared minus negative r squared. That's equal to 0. So because I wrote it so badly and up against that little edge, I went ahead and rewrote it a little clearer. Now, on the other case, let's say I make a circle. Or let's say I make something that doesn't look like a circle at all and it doesn't correct me. Okay, that's a circle. That's pretty exciting.
Go. No, stop it.
Is that a dog or a cat or something?
I did not know I was unmuted. I'm sorry.
That's okay. I hate this. It keeps undoing making the shape tool right. It's really making me mad. Okay, do it right this time. There it is. Okay, that's good. Excellent. Okay, now I'm going to take my eraser and erase too much because, of course I am. Okay, and okay, so that's what we're looking at now. But in this case, I want YCM is, whoa, Nelly, now you're right here. That's so helpful. Thank you so much. Thank you. That's really helpful. Okay. Y center of mass is equal to the integral of YDM over the integral of DM. Okay. Now, in this case, I'm going to go up here to Y and I'm going to draw another rectangle like so. And remember, the equation for a circle is x squared plus y squared equals r squared. That's what I'm actually using here. And if I chose to solve for x, I would get r squared minus y squared. So this is going to be negative square root r squared minus y squared. And this is going to be positive square root r squared minus y squared. And that's what I got to integrate. Okay, so my dA is going to be square root r squared minus y squared minus the negative square root r squared minus y squared. So that's the width times dy. Does that make sense? Now, luckily, that's beautiful because that just becomes twice that. So that's super helpful. So the top integral, the integral of y dm, is going to become integral of y. Now I've got to do sigma times dA, so I'll put my sigma in there. And then I'm going to say 2 times the square root r squared minus y squared dy. And I'm going to integrate this. And this time it will be correct to say from y equals 0 to r. Okay. And now I am going to say, let u equal r squared minus y squared, then du is equal to negative 2y dy. This case, I already have the 2 and the y. So all I need is to put a negative in front of it. Oops. So I'm going to say negative sigma times the integral of u to the 1/2 du. And that's going to give me negative sigma. Now it becomes the integral of u to 1/2 equals the integral equals u to the 3/2 divided by 3/2, which is 2/3. So I'm going to say it's going to be 2/3. And now I'm going to say this would be r squared minus, in the top case, we had y equals r, so it'd be r squared to the 3/2 power minus r squared minus 0 to the 3/2. Okay, clearly that first one's 0. The second one's not. In fact, it comes out to be r cubed, and we get negative 2 sigma, or actually we get positive 2 sigma r cubed over 3. But that's just the top part. Now we got to do the integral dm. And this one's not going to be as friendly because it doesn't have the y out there. So I got to do that trig substitution. In this case, I'm going to have sigma times the integral of 2 square root r squared minus y squared dy. I'm going to let y equal r sine theta. Then dy is equal to r cosine theta d theta. So I get sigma times 2 times the integral of the square root of r squared times 1 minus sine squared theta times another r times cosine theta d theta. Now you can see the r squared under the square root is just going to become plain r, and then another r. So I got 2 sigma r squared times the integral of this 1 minus sine squared is cosine squared. So when I take the square root, it's just going to become cosine. So I got cosine squared theta d theta. Okay. Now that gives me 2 sigma r squared times 1/2, because I'm using that identity that we just did, of 1 plus cosine 2 theta d theta. So the integral of d theta, I mean, when I distribute that d theta times 1, the integral of that part is just going to become theta. So that's going to say equal to 2 sigma. I don't know why I didn't go ahead and cancel out the 2, but I didn't. So I'll just leave that there for right now. When y was equal to 0, you can see that theta should be 0. And when y was equal to r, you can see that theta should be pi over 2. So I'm going to say 0 and pi over 2 for that range of integration. I know I just barely fit that in there, but I just wanted to do that for right now. So now I have all that times pi over 2 minus 0. That's for the integral of the 1. Now I'm going to get plus 1/2. And the 1/2 comes from the fact that I got to do a substitution 2 theta. Let's say W equals 2 theta, then dW equals 2 d theta. So I got to multiply d theta times 2, which means I also have to multiply by 1/2, and that's what that's for. And now I get the integral of cosine is just sine. So I'm going to get the sine of 2 times pi over 2 minus the sine of 2 times 0. So obviously you can see both of these are 0. And in fact, I get, for this result, I get sigma pi r squared over 2. So that means y center of mass, if I go up to here now, I'm going to take that top answer, which was 2 sigma r cubed over 3, and divide it by the bottom answer. Let's do that over again. And the bottom answer was sigma pi r squared over 2. You can see now that this 2 is going to cancel out with that 2. This sigma is going to cancel out with this sigma. And these 2 here is going to cancel out with that, leaving a 1. So I get that the answer is, actually, those 2's are not going to cancel out. They're actually going to multiply. Doop-a-doo. I'm going to go back a bunch of steps. When I divide by that fraction, the 2 comes on the top. So it's actually going to give me, it's actually going to be equal to 4 over 3 pi r. What happened was, again, this sigma canceled out with this sigma. This r squared cancel out with this, leaving just a 1. And then I had 2 times 2 on the top over 3 times pi on the bottom. So it's 4 r over 3 pi. So the center of mass of this thing is 0, 4 over 3 pi r xcm ycm. Any questions on that? So now we know that if we go to 4 over 3 pi is roughly what, 9? What, it's 9.42, yeah, roughly 9.42, something like that. So 4 over 9.42 is obviously a little bit less than half. So we're going to go a little bit less than halfway up the y-axis from the origin and keep our finger on the y-axis, and that's roughly where we're going to balance our half of a pizza. Does that make sense? Any questions on that one? All right, so that's a pretty robust center of mass calculation. Let's do a little simpler one. And this is probably one, if you've had statics or if you're currently taking statics, then you've clearly done this before. Instead of doing the simple version, I'm going to do the slightly harder version. So I'm going to start off by drawing a coordinate system. Okay, I got a problem here. I've got my pen color. I chose my pen, and I'm trying to push the shape tool so it'll automatically auto do it, but it keeps taking it away from pen. I guess that's okay. I'm going to pretend like it is and see what happens. There's my y-axis. And there's my x-axis. Now I'm going to take it just to the pen. So I can do this, and this will be y, and this will be x. And if I drew the diagonal going from the origin up and to the right, that's sort of the easier way in some sense. I'm going to draw it like this. So I'm going to say this is a uniform density, homogeneous lamina is the fancy word that they use in mathematics. And what I mean by that is sigma, which is the total mass divided by h times w and then times 2, because remember the area is 1/2 h times w. I'm going to find the center of mass of this. Okay, so we're pretending we know all three of those parameters, and therefore we could easily calculate sigma if we needed to. Okay, now the x center of mass is supposed to be integral of x dm over the integral of dm. So what I'm going to do is I'm going to choose right here, let that be x, let this be x plus dx, and then of course this height is just that function. Well, that function is y equals negative h over w x plus h. Does everybody understand how I got that for the y? So I'm just using y equals mx plus b, where m is the slope and b is the y-intercept. It clearly has a y-intercept of h. The slope is clearly negative, and the rise is h, and the run is w, but actually one of them has to be negative. That's how it makes it a negative. So anyways, that's what it is. So the dm is going to be sigma dA, which is sigma times negative h over w x plus h times dx. So that's what our DM is. Again, the x center of mass is the integral x dm over the integral of dm. So let's do the integral of x dm first. That's going to be, I'm going to go ahead and pull the sigma out in front, and I'm going to say it's going to be equal to the integral of x times negative h over w x plus h dx, which is going to equal the, let's get rid of that. It's going to equal sigma times the integral of negative h over w x squared plus hx dx. And that's going to be integrated from x equals 0 to w. This time I'm actually doing it right. I am going from x equals 0 to x equal w, and that's correct. So we're going to run with that. That's going to give me sigma times negative h over 2w, or excuse me, 3w, times w cubed, and then plus this would be h over 2 w squared. So I get sigma times, notice the w cubed cancels out with the w in the bottom, and that gives me negative h w squared over 3 plus h w squared over 2. If I got a common denominator, that would be negative 2/6 plus 3/6. So that's positive 1/6. So I'm going to get sigma h w squared over 6. Everybody agree with that? So 3/6 minus 2/6 is just positive 1/6. So that's right. That now I got to do the integral of dm. I want to stay in blue, darn you. So the integral of dm is still going to have my sigma, but now it's not going to have that extra h. It's just going to, I mean, that extra x. It's just going to be negative h over w x plus h dx from 0 to w. That's going to give me sigma times negative h over 2w w squared plus h w, like that. So that gives me sigma times this w in the top cancels out with w in the bottom, so I get a hw on top, and it's negative 1/2, so negative hw over 2 plus hw. So 1 minus 1/2 is obviously 1/2, so that'd be sigma hw over 2. So x center of mass is now sigma h w squared over 6 divided by sigma h w over 2. So you can see that it does turn out to be, hopefully what you learned in your statics class is it's always 1/3 of the way from the thickest part. So I expect the x center of mass to be 1/3 w, the y center of mass to be 1/3 h. And lo and behold, what you get here is 2 over 6. What's happening is this is canceled out with that, and this h and this w is canceling out with this h and this w. So I get 1/3 w. Whoa. And why I'm writing in blue, I read, I don't know. So that's our x center of mass. Any questions on that? Now, technically what I was doing with using that rectangle, in case, for instance, if I had this as a triangle, not like it's drawn now, but let's say we had a triangle that was like this. Then what I do is find the equation for y for the red line and do the equation for y for the blue line minus the equation for the red line. And that would be what's happening. So I wanted you to understand that, because really what I did here was I said y minus 0. I just didn't have to show the 0. But that's really what's going on there. I had to get that height, and that height happened to be y minus 0 because the bottom edge was at y equals 0. So if we had a more complex shape like the triangle I'm sort of outlined here by putting red lines, then you'd have to do negative h over w x plus h minus, and maybe that other equation was 2x minus 4. I say minus parentheses 2x minus 4. Okay. All right, everybody understand that part? Now the YCM is the integral of y dm over the integral of dm. You can actually use the same dm, which we got, of course, was integral dm. You can still use that if you want for the next part. I'm going to leave this up to you, and in fact, I'm going to make it an extra credit. So you'll see up posted an extra credit for you to do the whole thing. Now I will give you a little starter. Well, what happened? Okay, stop that. Okay, so now I'm going to say this edge right here is y, and I go out here and I draw a rectangle that way. And of course, this point is y plus dy. So you can see this rectangle is actually a height dy, but the width is in fact the x coordinate minus 0. So what I got to do now is solve this expression right here. I got to solve for x. For YCM. So in other words, what you're going to do is say your dA is dy times whatever you get when you solve that equation for x. So I'm giving you a big hint on getting that started. Again, this will erase your lowest homework grade. And in fact, every time I do one, I add another homework grade that I'm dropping. So this will fix all that. Okay, so all you have to do now is recalculate. You can copy, but I'd really recommend, because this is going to be actually on your final, maybe even your next test, you need to know how to do these integrals. So I highly recommend you try to figure out how to do this from scratch without looking at my work. And you might even find a different way of doing it, and that's fine too. If you've had, for instance, Calc 3, you might even try double integrals, because whenever you're integrating an area, it's sometimes a lot easier to do double integrals, especially when you have spherical or cylindrical symmetry. But the main thing is you've got to calculate XCM and YCM. And what I'd recommend you doing is try to do it on your own. If you can't, open up this, look at my calculation of XDM, try to make sense of it, close it, try to do it again on your own. When you get stuck, open it back up, look at what I did, see how you deviated from that, see what you got to do to fix it, and then try it again. Keep doing that until you get that right, then try the Y. Okay, any questions on that? All right, so I think that's enough of chapter 10. What I want to show you now is, or excuse me, of chapter 9. What I want to show you now is I want to go into rotational motion, and I'm going to do it by making a big parallel. But I'm going to start with a part that maybe you hadn't thought about too much. So first thing, we know from trigonometry
that if you have a circle, okay, and let's say that circle has a radius r, then this little arc length from here to here is s given by r times theta, where theta is measured in radians. Right? But what can you tell me about ds over dt? What would that be?
A speed or velocity.
Exactly. So we're going to call that v equals ds dt. But if it actually is on a circle, then the r is a constant. So we're just going to get r d theta dt. And we define a quantity, omega, is defined to be d theta over dt. And that's called your angular speed. It's often measured in units of radians per second.
And in fact, if you use radians, they will always work. But there's a lot of times where you can actually use degrees or whatever, and it works as well. What I did when I was first learning this is I just assumed I had to convert everything to radians. And then I watched over time and I could see, oh, well, if I use theta, the conversion from theta in degrees to theta in radians would have canceled each other out. Then I knew I could have used degrees there. So over time, you'll get that. Right now, don't worry about it.
Now, what is dv dt? Anybody know that?
It wouldn't be, is it tangential acceleration?
It is. It's a, and I put the little t on there just to remind you it's tangential. But that's true about this too. So if you're actually a car
Riding in a circle, this is what your speedometer is reading.
so this is tangential. And I usually don't even put the subscript t on it. I just call it a. But again, since v was r d theta dt, or r omega, we get that this is going to be r d omega dt, and we define a quantity alpha, which is equal to d omega over dt, and that's called your angular acceleration. And the units for that would be radians per second every second, which is mathematically equivalent to radians per second squared.
Again, this is one of those things where radians always works, but if you pay attention over time, you'll see that there's a lot of times where you don't have to use it. That's just something where you need a little bit more experience. Okay. So this alpha here is angular acceleration. And for instance, a typical angular speed, omega, is what we used to do, for instance, for our music, you know, because we're old. We had record players, which y'all call vinyl, I guess. You had vinyl record players, and they had speeds like 33 1/3 and 45 and stuff like that. What those were was revolutions per minute. So 33 1/3 revolutions per minute meant that its delta theta was 33.33333 rotations every 60 seconds. You can convert that to radians easily and use that sort of stuff, but that's a typical example of an angular speed is how fast it's rotating, or what's your tachometer in your car say. So the RPMs is another measure of omega. Revolutions per minute means 2 pi radians per minute. Okay, so that's what omega is. Now, if you took your vinyl, your record player, you might switch it from 33 1/3 to 45. And I don't even remember if 45 was really one of the speeds. That's just a number that came to me just now. So if I switch that from 33 1/3 to 45, and it took let's say it took 2 seconds to get up to that new angular speed, then my average alpha, my average angular acceleration would be 45 minus 33.33333 over 2. Well, let's call it 45.0 minus 33.3. That's going to be 6.7 plus 5. That's going to be 11.7 over 2. So that's going to be 5.85. So that's roughly 5.85 revolutions per second, or excuse me, per minute per second. So that's an actual unit of angular acceleration. It's a weird one. It's not unlike the 15 miles per hour per second that we got for the acceleration of a car that does 0 to 60 in 4 seconds. Okay, see how it's mixed 15 miles per hour per second. So this was what I say 5.85 revolutions per minute per second. So that's another example of it. Now here's the neat thing. All the stuff we learned that, for instance, x is equal to x0 plus v bar t. And we learned that v bar was equal to x minus x0 over t minus t0, right? We learned that v is equal to v0 plus a bar t, and a bar was v minus v0 over t. And we learned that x is equal to 1/2 a t squared plus v0 t plus x0. And we learned that v squared is equal to v0 squared plus 2 times a times x minus x0. We also learned that another version of v average would be v1 plus v2 over 2. Basically, these were only true for a equals a constant. Okay, but that's okay. That's all well and good. We've got that. But guess what? There's an exactly analogous version to all of these. There is theta is equal to theta 0 plus omega bar t. There is omega bar is equal to theta minus theta 0 over t minus t0. There is omega is equal to omega 0 plus alpha bar t. And there is alpha bar is equal to omega minus omega 0 over t. There is theta is equal to 1/2 alpha t squared plus omega 0 t plus theta 0. There's omega squared is equal to omega 0 squared plus 2 alpha theta minus theta 0. And there is also omega bar is equal to omega 1 plus omega 2 over 2. But there's also Newton's second law, the summation. Ooh, let's not do that. I can't stand that. Ooh. Now there's also Newton's second law, the summation of forces equals mass times acceleration, which is also mass times dv dt. There's also summation of forces is equal to dp dt. Well, there's a rotational analog to that, and it's the summation of the torques is equal to I times alpha, or it's equal to I times d omega over dt. And there's also the summation of the torques is equal to dl dt, where torque is defined to be r cross f, and L is defined to be R cross P. And I is equal to the integral of R squared dm. Now, if you had discrete objects, like little objects maybe that are really heavy and they're sitting on a rod that's kind of light, but they're secured to it, then it could just be M1 R1 squared plus M2 R2 squared plus M3 R3 squared, that sort of thing. But in general, you have to know how to do the intervals as well. So I'm going to go on the assumption that you guys are like experts at using those first 1, 2, 3, 4, 5, 6, 7 equations, right? And I'm going to jump into showing you how to use the Newton's second law equivalent. Obviously, you might need some explanation what R is. R is called the lever arm, and it's a vector that points from what you're calling the center of rotation to the point of application where the force is. And from your knowledge of the cross product, you probably can recognize that that could be R perpendicular times F, or it could be R times F perpendicular, or it could be R times F times the sine of theta. But in all those cases, because it's a cross product, the direction is actually perpendicular to both the R vector and the F vector. Similarly, the angular momentum vector, this L here that I have drawn, that is R cross P. And of course, that is also perpendicular to R and P. If you happen to drive a motorcycle and you took the motorcycle safety class, you would have learned something very odd, at least something that I thought was very odd, having ridden motorcycles and bikes forever. When you're riding down the highway and you want to say switch to the left lane from the right lane, my instinct was I just lean over to the left and that would pull me over to the left. What they said, get this now, you would take, again, I'm trying to switch from the right lane to the left lane. They told me to take my left hand and push forward on the left handlebar, the left side of the handlebar. And they're absolutely right. It does work. What actually happens there is you're applying a torque in the, basically the direction for this case would be down. You're applying a downward torque. That causes the bike to tip over to the left. The radius of curvature when the bikes tip to the left is a little bit smaller, so it actually causes you to turn to the left, even though you technically turned your handlebar to the right. But that's all because of this crazy torque thing. So I just thought I'd bring that up. It's kind of interesting to do that. So let's work. What I warned you about was the daughter of all Atwood machines. Okay. So instead of the mother of all Atwoods, this is the daughter of all Atwoods. So I'm going to do it all in terms of symbols, and then I'll give us some numbers and we can, do that as well. I'm going to say I have a circle right here. I have a tension there. I have a tension here. I have a box here and a box here. I'm going to say this radius is R. I'm going to say this box has a mass big M. This box has a mass little m. And I'm going to say this has a mass big M times P. And I'm going to say it's a cylinder. Of thickness H, which means that rho, the actual density, would be MP over pi r squared H. Okay. Let's say that M is going to be 100.0 kilograms. Let's say little m is going to be 5.00 kilograms. And let's say R is going to be 12.0 centimeters. And let's say there is a friction force acting at tangentially to the edge. Whoa, I don't know what happened there.
let's say F is going to be 5.00 newtons. Okay. All right, so how do we solve such a problem? Well, first I'm going to draw a free body diagram for the little mass, little m, and I'm going to go on the assumption that because the big mass was using a big M, that's going to go down, and I'm going to call that the positive direction. So that means the little mass going up is also the positive direction. So I'm going to actually call this tension here the tension in the left-hand side. Now, here's the reason for that. When you get to the tension on the right-hand side, that tension is going to be not only lifting the little mass M up, but it's also going to have to rotate the massive pulley. The pulley has mass now, and the pulley has friction. So the mass, the tension on the right is responsible for counteracting friction. It's responsible for rotating a massive pulley, and it's responsible for lifting up a mass, little m. So that's why I am going to have to label it different from the TL. That's the positive direction. Now I'm also going to have mg in the negative direction. So this is going to be negative mg, and I get the first equation of motion, which is TL minus mg is equal to m times a. Now, the actual string is not going to stretch or become slack or anything like that. So because of that, we can assume that the acceleration of the right block is the same as the acceleration of the left block. Does that make sense? So that's why I didn't subscript a with anything. Now I got to do a free body diagram for the mass big M. And that's going to be, in fact, whoa, what did I just do? Oh, I skipped. So it was okay. So now I'm going to have on this side a force of mg in the positive direction, but a force of negative TR that way. So now I've got mg minus TR is equal to big M times A. That's going to be equation 2. And I've got 3 unknowns, TL, TR, and A, and only 2 equations. Okay. That's okay. We got more to come. All right. Now I've got a free body diagram for the pulley. And yes, you suck. Got a free body diagram for the pulley, whose radius is, of course, R. And that is that TL pulls down this way, and T right pulls down this way. And in fact, what I've got to do is, since M going down is considered the positive direction, I'm going to consider this rotation as positive. Okay. Now we do have a friction force acting, so I'm also going to have to add a force of F right here going that way. Does everybody see the actual pulley is going to rotate clockwise because we suspect M being so much bigger than little m. It's going to cause it to go that way. And then friction opposes the relative motion of the moving part. So you can sort of picture this friction as like a little piece of wood sticking out of the wall, rubbing against the top of the pulley. Obviously, that would tend to make it slow down. So it's actually acting in a counterclockwise way. So now I'm going to use Newton's second law of motion, but in rotational form. Now, luckily, the forces F, TL, and TR are all perpendicular to the line from the center of rotation to the point of application of the force. So it's just R times the force. I don't have to use a sign or a cross product or anything like that. So I'm also going to keep the signs consistent. So I'm going to say equation 3 is, in fact, R times TR minus R times TL minus R times F is equal to I times alpha.
Well, old poop, we don't know what I is.
And now we've got 1, 2, 3, 4
Unknowns. We got TL, T right, A, that's 3. I, we don't know that when I'm getting ready to work it out though, so I'm going to leave that off. And then alpha. Okay. But luckily there's a relationship as long as we assume the string is not slipping along the pulley. Okay. If the string is not slipping along the pulley, then we know A is equal to R times alpha. And that's equation 4. So without slipping. And that's the worst looking L I've ever drawn. Okay. Now, what is I? I said I is equal to the integral of R squared dm. So now you're getting an extra problem. Okay. I'm going to actually do it. I'm going to say this is my x-axis or y-axis. This is my x-axis. And this is my z-axis, like so. And I'm going to draw a cylinder like so. Okay. Now my dm is going to be rho dv. And of course, rho is just going to be, like I said up there, mp over power squared h. We already know that. So what I'm going to use for my dv is I'm going to take a thin circular slice like this, and then extend it downwards to the bottom. So that dv is equal to 2 pi r. That's the distance around. And if I multiply that by dr, that's the surface area of the top. And then if I multiply that by h, then that's the volume of that shape. Does that make sense to everybody?
So I is going to be equal to, I can go ahead and pull the rho and the 2 pi and the h out. So I'm going to say 2 pi h rho, pulling that out in front, is equal to the integral of r squared. Now I've already taken out the 2 pi and the h, so all I have left is the r dr, and I'm going to integrate that from r equals 0 to big R. That's obviously r cubed. So I get 2 pi h rho times 1/4 r to the 4th. So my moment of inertia, I, is equal to 2 times pi times h over r, or excuse me, over 4. Times r to the 4th. And now my rho, I already said, was mp over pi r squared h, right? So I think you can see that for starters, this 2 is going to cancel out that, leaving that a 2, and I'm going to have 1/2 mp r squared.
And that's the actual formula for any cylinder of any thickness. The moment of inertia rotated about its central symmetry axis is 1/2 mr squared. Okay.
So I'm going to write down equation 5. I is equal to 1/2 mp r squared.
Now, we've got these nice equations. What I'm going to do is I'm going to go ahead and plug 4 and 5 into 3. So plug 4 and 5 into 3. And what that's going to give me is RTR minus RTL minus RF is equal to 1/2 MPR squared times R times A. You can obviously see that this R is going to cancel out. Right? So I now have TR minus TL minus F is equal to 1/2 MP times R times A. And that's going to be equation 6. Now what I'm going to do is subtract equation 2 from equation 1. So, come here. Subtract 2 from 1. Well, if you look, 2 is mg, big mg minus tr over m. So I'm going to say negative mg plus tr equals minus ma. That takes care of the minus part. In other words, I just flipped the sign. The other one was TL minus mg is equal to ma. I was supposed to write an A there, not a G. So when I add these together, I end up getting, is that right? TL minus TR. That did not give me what I wanted. What I was trying to get is TR minus TL or TL minus TR. So let me look back at the thing again and see what I'm going to do. Okay. I'll just add 1 and 2. So let's do that. We'll say add . So when I add 1 and 2, notice I get TL minus MG is equal to MA, and MG minus TR is equal to big MA. So when I add them, I get TL minus TR, and then plus M minus M times G is equal to M plus M times A. And that'll be equation 7. So I can say that TL minus TR is equal to M plus M times A minus M times G. That'll be equation 7 prime. Okay. Now, if I look back at my equation, what did I call that equation? I think I called it equation 6, right? I think I called it 6, but never wrote it down evidently. So let me write it down now. This is equation 6. So that's TR minus TL. So I really got to do the negative of that. But basically, now that I have TL minus TR, I can put that in there. And that's equal to 1/2 MPRA. So I'm going to say 7
into 6, that's going to give me m minus m times g minus m plus m times a minus f is equal to 1/2 mp times r times a. So in this case, the only unknown we have is a. So I can go ahead and take that over there. I'm going to say m minus m times g minus f is equal to 1/2 mp. I'm really bothered by this r being in there. I think I might have made an arithmetic mistake earlier. I'm going to check that in a second, but we see over here, I'm going to go ahead and call it RA and see what plays out. But I'm pulling the m plus m over here. That'll become positive. So I'll say plus, actually, I'm going to factor out the a, and then I'm going to address that pesky r because I think that r is not supposed to be there. So it's going to be 1/2 mp times r. When I pull it over there, it'll be plus. So it'll be plus m plus big M, all that times a. So a would be m minus m g minus f over m plus m plus 1/2 mp times r. So you can see right there, that's clearly not the case. Now I'm going to go back and fix that. Notice back here, a equals r times alpha is the equation we're using. Notice this guy right here. And this equation right here, I substituted r times a instead of a over r. So this is the error. I'm going to say now what happened was that's supposed to be a over r. So if I put the correction as r here, then everything works out really nicely, because that r is going to cancel out one of those r's, and this r is going to be completely gone now. So this is not supposed to be there, and that's really the only change we have to do. Yeah, that's the only change we have to do. So that means now, where is that? I didn't use it there. This is gone, and this is gone. So the actual correct answer is this without that r there. So a is equal to m minus m parentheses g minus f over m plus 1/2 mp. All of that times g. Oh, no, I already included the g in there. So that's the acceleration. We have that. Now that we have the acceleration, we can plug into 1 to get t left, or tr, I think. And we can plug it into 2 to get t left. And we can plug it into, I think it was equation 3, and get alpha as well. Okay, once you know TL and TR, you can plug that in and find alpha too. So all right, so that is the daughter of all Atwood machines. Any questions on that one? I'm going to leave that as extra credit.
So that's another extra credit assignment I'm gonna give you guys. Okay, that should be pretty straightforward. I'll have 2 turn-in spots for that on this week's module, and you'll be able to see that. Don't worry too much about making the algebra pretty. If you can get a nice pretty expression, by all means do, but I don't want you wasting a whole lot of time on it. I just want you filling it in, and I've sort of spelled out what you got to do. You're going to take that out, that A, and plug it into equation 1, and then the only unknown is the tension. And then you take that A and plug it into equation 2, and the only unknown is the other tension. And then, of course, now you have both the tensions. You can plug them into the equation of motion for the actual pulley. And that can allow you to get alpha. Or you could just take and realize that alpha is just R times A. Or excuse me, A is just R times alpha. So if you divided this alpha by R, this A by R, you'd get alpha as well, but that's a little less helpful. So anyways, make sure you catch that. Oh, now I still got the green pen. There was an R that appeared here too that shouldn't be. Anybody see any other R's next to the MP? I think that's it. So that was the correction I made. I'm sorry I made the mistake in the first place. It was bothering me when I kept running into it. I was expecting it to cancel out, and that's what happened. I had written R times alpha instead of or excuse me, R times A instead of A over R. So any questions on that one? All right, so that is some of the stuff we can do. Now, once you have that tension, or excuse me, that acceleration, now I can do stuff like what is A? So I've actually got a formula now for A, and I've got all the actual numbers for A. So A is going to be equal to M minus M, that's 100 minus 10. So that's 100 minus 10 times 9.80 meters per second every second. And this is kilograms, minus the friction force, which I think I said was 5 newtons. Oh, I said M was 5 kilograms, not 10. Sorry about that. The friction force I did say was 5 newtons. So let me fix that. So this is going to be 100 minus 5 kilograms times 9.8 minus. Now I don't forget what friction was. Crap. The friction force was 5 newtons. Duh. It was the same number. 5.00 newtons over 100 plus 5.00 kilograms plus 1/2 of what was the mass of the pulley. I think I said the mass of the pulley. Oh, I did not specify that. So I'm going to say MP is equal to 3.00 kilograms. So 3.00 kilograms. What we're going to get is 95 times 9.8. So 95 times 9.8. And then I'm going to subtract from that 5. That's 931 minus 5 is 926. And then I'm going to divide that by parentheses 100 plus 5 plus 0.5 times 3. And that's going to give me 8.69 meters per second every second. So that's the acceleration. Now I can say, how far will M
fall after 1.00 seconds? Well, that's a simple theta equals 1/2 alpha t squared. Actually, I should, when I word it like that, I really shouldn't say it that way. So I'm going to do this. First off, I'm going to say how far is x is equal to 1/2 a t squared plus v0 t plus x0. So I'm going to go on the assumption that the initial position was 0. And since it fell, that means we let it go. So that's 0 as well. So the distance it's actually going to travel is 1/2 of 8.69 meters per second every second times 1.00 seconds squared. So I'll say 0.5 times, that gives me 4.35 meters is how far it would travel. And now I can say how much will the pulley rotate in 1.00 seconds? Well, that's where you use theta is equal to 1/2 alpha t squared plus omega 0 t plus theta 0. Again, that 0 and that 0. So I get 1/2 of alpha, which is equal to a over r. So that's 8.69 meters per second over 0.120 meters, that's the r, times 1.00 seconds squared. That's going to be divided by 0.12 times 0.5. That gives me 42.0 radians is what it's going to turn through. And then I'd say, well, times pi radians is equal to 180 degrees. So I'd say times 180 and then divided by 3.14159. And that gives me, well, that's pretty big, 2,407.86 degrees. Okay, obviously, I should only be rounding that to 2,410 or 2.41 times 10 to the third degrees. I could also say what I could say, what is M's speed at 1.00 seconds, and how fast is the pulley rotating at 1.00 seconds. Okay, this one's just a V equals V0 plus AT. We did find that it was a constant acceleration, and the V0 is 0. So it's just going to be 8.69 meters per second times 1.00 seconds, which equals 8.69 meters per second. This one's just, you can use omega equals omega 0 plus alpha t if you want it. And again, this part is 0, just like that one was 0 there. So I'm ended up getting 8.69 meters per second divided by 0.12 meters. Again, I'm using A is equal to R times alpha, but times 1.00 seconds, and I get 72.5 radians per second, which again, I can do 180 over pi. And that's 4,150 degrees per second. But a more meaningful one is really, if I divide that by 360, then that'd be revolutions per second. So that's 11.53. I'll just call it 11.5 revolutions per second. If you wanted it per minute, you could multiply that by 60, and then you get 692 RPMs. That's really getting bad there. So anyways, that's some other figures you could use. But wow, that's really Christmassy looking, isn't it? So I apologize writing up along that edge there, but I just wanted to show you some different, units that we could use for rotation. And those are, in fact, when you talk about revolutions per second or revolutions per minute, then you're actually talking in terms of, if you go to the Home Depot, they'll tell you, for instance, a particular impact wrench or a particular drill will have a certain number of revolutions per minute or revolutions per second. So those are more like units you're used to. Okay. Any questions on that? So now I've done some kinematics and I've done some actual dynamics by actually using, Newton's third law in rotational form. I just want to point out that another version of torque. Dang it! I can't make this over. It's like it doesn't recognize my capacitance of my fingers. Come. There's got to be an easier way. Come on. There you go. Okay. So remember, torque is equal to R cross F. So if you're imagining, say, a circle, that would be a nut, right? And it would actually have a actually I should do like this, say, well, that went bad. Okay, so let's pretend that's a nut. And I've got a wrench connected to it. A crappy wrench. Like this, okay? If I'm actually applying the force, say this way, then that's the R vector. And what we do is we'd say R F, and this would be the angle theta. Then torque would equal R times F times the sine of theta.
But if you look at that, you can realize that this F could have a component this way that's F parallel, and then it could have a component this way that's F perpendicular. So you get R times F perp. However, you could also say that R, the R vector, okay, the R vector could have a component this way, which is R parallel to F, and then it could have a component this way, which is R perpendicular to F. In that case, you could see it's R perpendicular times F.
Can you repeat the last part, what you just said?
Okay, so you recognize the R vector is the same R vector I had drawn in the wrench above, and the F vector is supposed to be the same F vector that I had drawn above. So the R vector, you can consider it as made up of two perpendicular components. One component is parallel to the F, and I called that R parallel, which is the one on the left. And the other component is actually perpendicular to F, and I called that R perp. That's the one on the right. So the torque can also be written as R perpendicular times F, meaning the component of R that's perpendicular times F, or that's perpendicular to F, multiplied by F is the torque.
Okay. Thank
Those
you.
are quick and dirty ways to help you not have to use a cross product, in other words. Okay. Now, something else I want to discuss with you was just like when we had the summation of Newton's forces is equal to dp dt. Remember, I told you that's the correct, more correct version of Newton's second law. What we found is when the summation of the forces is equal to 0, then dp dt is equal to 0, which means P equals a constant. Right? Well, guess what? The summation of the torques is equal to dl dt. So when the summation of the torques is equal to 0, then L is equal to a constant. L, like I said, was R cross P. But just like P is equal to MV, you can also pretend there's a vector omega, and you'd say L is equal to I times omega. So if the summation of the torques is equal to 0, then I times omega is equal to a constant. What does that mean? Well, that means when an ice skater's got her arms out like this, you could model her as, say, 85% of her mass is a cylinder of radius, basically the distance from her, where her Adam's apple would be to the outside edge of her shadow of her shoulder. And that would be 1/2 mr squared. But then she has a length of her arm where you'd pretend the center of mass of her arm is out where her elbow is. And each one of those is 7.5% of her mass. And you could say the cylinder is rotating this way. So her I, her moment of inertia, would be quite large. It would be 1/2 mr squared for 85% of her mass. Then it would be actually 1/3 L squared for each arm. And the L would actually be quite a bit larger than L. It'd be the distance from my spine to my elbow. And that I would be quite large. So we'd get large I, small omega when her arms are this way. Okay. And then when she brings her arms in, then we'd have small I and large omega. That's why. Okay. Even if you don't ice skate or roller skate, you've probably seen it on like a tire swing or a regular swing. If you're in a tire swing and someone starts spinning you around, you kick your legs out, it slows down. You kick your arms out too, you're probably going to fall off, but you could slow yourself down a little bit. If you bring them all tucked in really small, that'll make you go really, really fast. That's also part of how you swing on a swing set. With a swing set, you're normally setting, well, maybe you're setting like this, right? But if you take and push your legs down, then what that does is puts a little bit of your center of mass a little further out. So in fact, you could actually use that to slow yourself down if you wanted to. But if you started with your legs back here and then swung them forward as your mass went back, as your body went back that way, then you're putting all your mass right along here. You're sort of streamlining yourself from an angular momentum standpoint. All your mass, instead of having some of it near the hinge and some of it below the seat, you're having it all basically at the seat. And by doing so, you're actually allowing it to go really, really fast because your I has decreased. And then when you come back, you can actually just hold your feet up and that'll actually speed you up as well. So that's some of the conservation of angular momentum stuff. Another thing that might happen is, since I have red here, this could be the sun. And you could actually have an orbit of a planet right here. And this would be our perihelion from here to here. And this would be our aphelion. And this would be V aphelion. And this would be V perihelion. And I've actually drawn that incorrectly on purpose. Angular momentum L is R cross P, right? Since the R is very small over here, what we have is R, and they're perpendicular, R perihelion, V perihelion has to equal R aphelion, V aphelion. So that's another conservation of momentum, of angular momentum problem. But you can see, since this one's going to be big, then this one has to be small to account for that one, because this is small. So that's really, when I said Kepler's second law is that they sweep out equal areas in equal times, that shows you that the actual velocity is very high when you're near the sun, but very low when you're far away from the sun. So that's another typical problem you're going to have to be able to solve in the rotational motion stuff. Any questions on that? All right. Well, we've actually done enough, I think. I think between those examples that we did and the explanations that I gave you verbally, I think you can pretty much piece together all of chapter 10. Or excuse me, yeah, all of chapter 10. That's right. Next time, I will, of course, take questions on chapters 9 and 10. That'll be on Monday. And then a test will be on Wednesday, and another online test will be coming that week as well. Again, I told you there's definitely going to be a test Wednesday. I haven't decided which chapters that'll cover. And there's going to be a test, an online test that's probably going to be due Friday. If not, it'll be due the following Monday. And I don't mean this Friday, I mean next Friday. Okay. But both of those are going to be done, and the practice test will be posted. When I post the practice test, you'll see what I've chosen for as the order of the chapters and which chapter is going to be covered. So if anybody has any questions, you're welcome to stick around. If not, you're free to go. I'm letting you out a whole 8 minutes early. Woo-hoo! Thanks for coming, everybody.
Thanks, Professor. Have a good one.
You too.
Oh, wait, I have a question.
Go for it.
For the first extra credit, I don't remember what it was on. I think we were doing something with gravity, and we were calculating the gravitational constant, like different depths and stuff.
Oh yeah, you're talking about previous class.
Yeah. I'm still working on, is it okay if I turn that in this week?
Yeah, if it doesn't let you, just let me know and I'll change the dates. I try to keep those dates where it's only got a due date. It doesn't have a until date. I think the two that I made today, though, actually have an until date, because there's not much use for you doing them after we've had our tests. So that's what I
Gotcha.
want to do. Like, but yeah, if you still want to do those, you can turn them in at any time.
Okay, all right, yeah, the one that was for last class, the gravity one, that has like a set date, so it was closed, and when I went to go see if I could turn it in, I couldn't.
Gotcha. That was the gravity one.
Yeah,
I'll go ahead and fix that now then.
sweet, sweet. Okay,
Okay,
thank-
I'm in there. Anybody else have any questions while I'm doing that?
Question. I was wondering if you got my email that I sent you about the online test.
Who is this speaking with me? I'm looking. Is it Sarah?
It's Sarah.
Okay. I remember getting an email from you, but I'm not sure I read it, to be honest with you. Let me double check.
Gotcha. Okay, thanks.
What's going on with the is it something you want is it something you want to talk to me in a public situation or not? Yeah, I see.
Basically, yeah, okay. I was just saying basically I was asking what to do about it. Because I turned in the test and everything. I got a pretty good grade and I didn't know what to do.
Gotcha.
So I sent you an email.
Okay, I'll reply to that immediately. Okay. Thanks, Sarah.
Okay, thank you.
Anybody else? Okay, let's see, there's extra credit problem there. It's probably extra credit G in black holes. I think that's one. Oh yeah. Yeah, go for it. Casson, do you have a question?
Yeah, so I had you open up like the, I guess like the midterm practice test, but like that grade won't go in because of, I guess like the chapter 5-6 practice test. So how does that like work?
Okay, so you did take a practice midterm. Is that what you're saying?
Yeah, I took the practice midterm, but I guess like I didn't take like the chapter 5.
Okay. I didn't mean, let me see. I'm not sure I ever meant the chapter 5 and 6 practice test to ever be out there. So if you didn't take it, that's fine. It's not supposed to be out yet. So yeah, I would say, yeah, don't worry about that. That's not a big deal. It's you weren't supposed to do that anyways.
Okay, it just, I think it's right now. It just it has it missing, so then
Right.
it's gonna it puts in the 0.
Yeah, that's not going to count against you. I will make sure I weed that out when I do my final grades. Because I am going to actually make a test 5, but I think what happened is I made it available for a split second by accident, because when I open up a module and make it available to you guys, if the things inside of it are available, it automatically becomes available. And once it becomes available, it counts it as an object in the test bank. I mean, in the grade book. So it made it as if you took it, but no one took it. So you're okay. When I do open it, you taking it will either fix that it's a 0 or unless you got a 0, which you won't. So that'll be taken care of. But definitely check it like when at the end of the semester, like just before you do your final exam, make sure there's no zeros like that anymore. And then, you know, take a photograph of a screenshot or whatever of anything on your grade book on your side that shows a 0 on it, and send that to me, because you know I don't want that to be wrong. And if you catch me doing something like that, that'll be a good thing for me to correct. So feel free to do that at any time. Okay.
Okay.
All right. See you, Caston. Unless you had another question.